If you've ever broken a bone, had your teeth cleaned, or taken your pet to the vet, you've probably witnessed or experienced the process of X-ray imaging. But have you ever wondered how an X-ray actually works? To the uneducated mind, X-ray imaging seems rather similar to typical photography. A machine is pointed at you for a few seconds, and then it generates an image of you. But despite the sense of simplicity, X-ray imaging is much more complicated than that. X-rays model parts of the body that the human eye can't readily see. Radiation can be defined as the transport of thermal energy in the form of photons. A well-known example used to help understand radiation is the sun, which produces radiative energy in many different forms across the electromagnetic spectrum. Radiation is what is used in X-ray photography. There are 4 laws that govern radiative energy. These are Planck's law, Stefan Boltzmann's law, Wien's law, and Kirchhoff's law. However, all of these laws are derived from Planck's law, with Kirchhoff's law directly relating to Stefan Boltzmann law. Planck's law states that everything in the universe emits some form of radiation, meaning that all living things and inanimate objects are constantly emitting radiation around you.
The Planck's law equation presents the spectral radiance of a body, also known as its emission intensity, as a function of its absolute temperature and wave frequency, and it includes the Boltzmann constant, Planck's constant, and the speed of light in the medium in order to determine this relationship. Another law, known as Wien's law, elaborates on Planck's law and describes that a body at a higher temperature emits higher intensity radiation at a specific wavelength. Therefore, as temperature increases, the wavelength of radiation from a body decreases. As you can see from the graph, Planck's law and Wien's law are very closely related, but Wien's law corrects intensity of emission compared to Planck's law. Stefan Boltzmann's law relates area and temperature to power emitted, such that the total amount of power per unit area is proportional to the 4th power of temperature difference. Depicted on the graph is the effect of emissivity on radiation power. A perfect emitter boasts of an emissivity of 1, and as the emissivity becomes closer to 1, the power released increases. Kirchhoff's law addresses non-perfect emitters and states that at a constant temperature, if a body absorbs an amount of radiation, it can emit the same amount of radiation. In conjunction with Stefan Boltzmann's law, Kirchhoff's law explains the link between emission and absorption.
X-ray radiation not only follows Planck's law, Wien's law, Stefan Boltzmann's law, and Kirchhoff's law, but it also functions on another law known as Bragg's law. Bragg's law describes the angle of X-ray diffraction from a crystalline solid, such as bone. X-rays can pass through non-crystalline, non-solid materials like blood and saline, but bounce off of a bone at a diffracted angle. Using Bragg's law of angle diffraction, computers analyze the diffracted X-rays and map it into a picture, modeling non-diffracting layers in a dark contrast to diffracted layers. For our calculations of X-ray radiative energy, however, we relied on the Stefan Boltzmann law, which relates the amount of power emitted with the emissivity, surface area, and temperature. For our simulation, we utilized the COMSOL physics engine to be able to easily visualize how these X-rays react when the patient has a lead plate protector. Listed here are the estimates and assumptions used within our calculations and COMSOL simulation. For the simulation, we used a tungsten X-ray emitter 30 centimeters away from a human arm, with the layers from left to right of lead, skin, blood, muscle, and bone. This simulation would allow us to get a better visual representation of how the X-rays react when contacting the lead protecting plate. Within our calculations, we aim to determine the potential effects of different X-ray scans on a human. We used the Stefan Boltzmann law to calculate the total energy being emitted from the tungsten. In addition, we related the amount of thermal energy transfer to the amount of energy due purely to the X-ray photons, using an equation indicating that X-rays make up about 1% of the total energy transfer. We then calculated the amount of energy required for each X-ray type and used this to determine the amount of time needed to complete each X-ray. Finally, we were able to calculate the equivalent days of regular daily exposure that each X-ray scan would have, using 0.01 millisieverts to be the estimated daily exposure that a human receives on a normal day. We found that most X-ray scans would not expose someone to more radiation than they would receive in a normal day or week, and should be no cause for concern. However, some of the more in-depth scans, like a spine X-ray, are equivalent to months of radiation and should be done sparingly and only when completely needed. In addition, we created a COMSOL simulation to determine how these values would likely change with the lead protector plate. And as you can see through the COMSOL simulation, the X-rays lost a lot of energy while going through the lead protector plate, and the actual values that a patient would be exposed to are much less than what we calculated with this protector plate.
But just as we are all aware of what X-ray photographs are, we also need to be aware of the dangers that follow along with radiation. Accidents due to uncontrolled radiation occurred at Chernobyl, 3 Mile Island, and Fukushima. These accidents resulted in immediate death of over 40,000 people, displacement of 700,000 people, and left 1,000 total miles of land uninhabitable. To this day, these areas continue to see mutations and birth defects of radiative poisoning. Well-known scientists Marie and Pierre Curie are referred to as the couple who coined radioactivity. Unfortunately, the consistent interaction with radioactive substances led to suffering immense amount of radiation exposure that led to Madame Curie's death. However, we have learned from these tragedies in order to find a safer way to use radiation, specifically in healthcare. According to Bragg's law, a crystalline solid will diffract radiation, so it can be concluded that crystalline solid materials should be used to protect the body from unneeded radiation. Additionally, applying Stephen Boltzmann's law and Kirchhoff's law suggests that the material must be able to absorb the wavelength that X-rays travel in order to protect the body. And using this knowledge, modern medicine now utilizes lead sheets to protect part of the body that are not being scanned. Lead's conductivity in solid structure enables its free electrons to redirect and diffuse radiative energy. Additionally, modern healthcare follows mitigative guidelines focused on duration and distance. The guiding principle of radiation use in healthcare is known as ALARA, or as low as reasonably achievable. Simply, this means that radiation should be used in the lowest amount possible to achieve effective results.